We're going to start today on day 2 of our notes, covering triangle midsegment. So the midsegment of a triangle is a segment connecting the midpoints of two sides of the triangle. So DE is the midsegment of this triangle over here to the right. A couple of things happen with our midsegment. If a segment joins the two midpoints of the two sides of a triangle, then the segment is parallel to the third side and half as long. So if we take a look at our picture here, DE will be parallel to AC, and DE will also be half of AC. So one way that we can write that is we can say that 2 times DE is equal to AC, or DE is equal to AC divided by 2, depending on which numbers you want to take half of or double. So if we take a look here at number 1, we're not going to do all of these examples because some of them are kind of monotonous. It says identify all pairs of parallel segments. So if I'm looking at XR, that will be parallel to WY. I guess I should change that to QR since that's the whole way across, but either way, that takes care of it. All right, so if I take a look at those two and move around my triangle, then XY is going to be parallel to QS, and XW is going to be parallel to RS. So remember that if these lines are parallel, we will have some corresponding angles that are congruent. So for example, this angle would be congruent to this angle. You would also have some some same side interior angles. So these here would be supplementary to each other because they are same side interior angles. All right, so L, M, and N are midpoints. So I'm going to stop there and I'm going to go ahead and mark my sides. So if L is the midpoint of PQ, that tells me that these two pieces are cut in half, and these two, and those two. And now let's go ahead and plug in our numbers. So PR is 46, so all the way across. PQ is 40. And LN is 17. So we can work our way down. If PQ is 40, then NM is half of that, or 20. If LN is 17, then the entire distance across will be 2 times that, or 34. And if PR is 46, then half of that will be LM, which is 23. So LM is 23, MN is 20, QR is 34, and MR will be half of that, 34, 17. On the rest of these examples, we'll have something like this. So remember that your midsegment is half of the long piece. So we actually will multiply this one by 2 to get its parallel corresponding piece. So 2 times 7x will equal 17x minus 18. Whenever I rearrange all of this, I end up with 14, so negative 3x whenever I bring over the 17 is equal to negative 18. X is equal to 6. Remember, you can always plug these in and double check them. So those are our mid-segments. For our perpendicular bisectors, we're going to hit a little bit on this page and then we're going to move down the list. So a perpendicular bisector theorem tells us that if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So if CD is perpendicular to AB and it cuts AB in half, then what we know is that the distance from CA is going to be equal to the distance from C to B. Now, this will be consistent anywhere along this line. So even if I move point C down the perpendicular bisector, I'm still going to have it be equidistant from the end points of my segment. So almost think of it like it's attached by a rubber band on both sides. CA and CB are rubber bands. No matter where I move that pink dot, those two pieces are going to be congruent. The converse of that tells us that if we know that CA and CB are congruent, then we know that CD is the perpendicular bisector of AB. So we know that CD and AB are perpendicular, and we also know that CD bisects AB. Now, these examples here are just basic algebra problems. You set them equal and you solve them based off of these being perpendicular bisectors. I'm going to skip these because I know that by this point you guys are really good about solving equations for a variable, and I want to get down to the good stuff. So we have our perpendicular bisectors, and the next thing that we're going to cover are our angle bisectors. So our angle bisector theorem tells us that if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. Now remember that distance is measured perpendicularly. So if AD bisects my angle and I'm looking at perpendicular distance, then BD and CD will be congruent to each other. For the converse, if I know that the perpendicular distance between D and B and D and C is congruent, then I know that AD bisects my angle. Now remember, if AD bisects angle BAC, that doesn't tell me segment lengths. That tells me that angle ABD is congruent to angle CAD. Okay, so remember that angle bisector tells us that two angles are congruent, not two segments. So same thing here. We're just going to set a bunch of things equal to each other, whether they are angles or segments, and solve for a variable. These are not the types of problems that we're going to give you, so I want to get down to the ones that we will. We're going to cover what are called points of concurrency. And using our perpendicular bisectors and our angle bisectors, we will be forming two different points of concurrency. So if you are taking a course in high school concurrently, you are taking them at the same time. And you're also, if you think about it this way, you're taking it where high school and college meet, okay? Now, what we use for our first point of concurrency are our perpendicular bisectors. So our perpendicular bisectors meet at what we call the circumcenter. This section of Unit 3 has a whole lot of vocab, so we've just got to make sure that we're really studying this. The perpendicular bisectors of the sides of a triangle intersect at what we call the circumcenter. That circumcenter is always equidistant from the vertices of our triangle. So if I look here, I'm going to use my highlighter, it's equidistant from the vertices. So if point P is my circumcenter, then point P out to B, P out to A, and P out to point C are all congruent to each other. Okay? Now, it is formed from the sides and is equidistant to the angles. So our perpendicular bisectors in this picture would be DP and EP and FP. Our circumcenter is point P. And our congruent segments. There are a lot of them, so one thing to take into account is that all of the sides are being split evenly, and that point is equidistant from the angles. So if we take a look at this picture here, Notice we don't have any markings, nothing's marked perpendicular, nothing's marked congruent, but what we do have is that Z is the circumcenter. So when I see this word, it is important that I recognize that it is the perpendicular bisectors. So these pieces are perpendicular and they are splitting our sides in half. And if it is formed from the sides, it is equidistant to the angles. So all of these green pieces are congruent to each other. This allows me to move around some numbers. So I can move my 19 here. I know that the 34 is split in half to be 17 and 17. And also this green segment of 21 can move into two other places. Now, the other thing that's going on here is that we have a whole bunch of right triangles. So depending on what pieces we're trying to find, we can use the Pythagorean theorem to do that. So let's see what it wants us to find. TU will be 19 times 2, so 38. VY is half of 34, which is 17. UZ is 21. It's that green segment that's congruent the whole way around. And WV we will have to find, and TV we will have to find. So if we focus our energy on this purple triangle here with the 15 and the 21, what we need to find is that length at the bottom for WV. So if I want to find WV, I'm going to use my Pythagorean theorem with 21 as my hypotenuse. So a squared plus b squared, which is 15, equals 21 squared. Now, the last thing I want you to do is to plug this all into your calculator and get a decimal. So what I want you to do is we'll go ahead and do our 21 squared minus the 15 squared. And I end up with a squared is equal to 216. Now, I don't want you to plug that in as a decimal. So what we'll do is we'll break this down. 216 divided by 6 is 36. So 6 times 36. 6 is 2 times 3. 36 is 6 times 6. Now remember that we're looking for pairs of numbers, so I'm actually going to stop there. And these two are left without a buddy. So I'm going to bring out the 2 times 3 as a 6, and a pair leaves the house as 1. So this 2 times 3 will stay home in the form of a 6, and 1 6 will leave. So VW is going to be 6 square root 6. And remember that if I do 2 times 6 square root 6, the 2 only gets applied to the outsider. So this becomes 12 square root 6 to get all the way across. It's the same thing with the rest of these. As soon as you know that you have a circumcenter, mark that your sides are congruent and being split in half. You have right angle. And then you also know that it is equidistant to the angles. So it is formed from the sides and is equidistant to the angles. And then again, we have this setup of a bunch of right triangles. So the next piece that we're going to use our angle bisectors. To create our incenter. So the incenter is formed from the angles and is equidistant from the sides of our triangle. So if we look at our picture over here, it's formed from the angles and is equidistant to the perpendicular piece on its side. So these three pieces would all be congruent to each other. Now, this is the incenter because if we're referring to point P as the center of our triangle and the incenter of our triangle, then point P can also be seen as the center of a circle that is inscribed inside of our triangle. Now, this circle is obviously not a great one, but what you would find if you did the constructions, which you'll do a little bit later, you'll find that that radius hits each side of our triangle perfectly. Whereas our circumcenter circumscribes our triangle, and this point ends up being the center of a circle that hits all three vertices. Now, these pictures are not perfect. They're pretty close. But that would be our circumscribed circle. Whereas this one down here, let me see if I can draw it one more time, is inscribed inside of our triangle. There we go, that's better. Okay, now, so our angle bisectors would be PB and PA and PC. Our in-center would be point P. And as far as congruent segments are concerned, we're just stuck with those four that are purple. All right, so if we look here, this one tells us that point P is the in-center. Now, when we have an in-center, we need to know that our angles are being bisected. And also that it is equidistant to the edges of my triangle. So all three of these pieces are congruent to each other. These perpendicular markings do not represent perpendicular bisectors. That represents the perpendicular distance from the center out to the edge. So all three of these purple pieces will be 8. And then it's just another matter of using Pythagorean theorem. Now, the cool thing about these is that these outer edges will wrap around, so this length over here will also be 17. And then we can work to find the measures that we need. So we need NP, so we'll use our Pythagorean theorem for that. 8 squared plus 17 squared is equal to C squared. So 17 squared plus 8 squared. This is 353. And when we take the square root of that, that's actually a prime number, so that will stay. So NP is the square root of 353. NK, we moved around to be 17. PK, oh, I'm sorry, I goofed that up. This part should be PK, that's my bad. NP was the 8. Sorry about that. And the last one we need to find is LO. So for LO, I have the 8 and the 13. The 13 is my hypotenuse. So I'm going to have 8 squared plus B squared is equal to 13 squared. And if I do 13 squared minus 8 squared, that gets me 105. So B squared is equal to 105. If I take that down, it's 21 times 5, 7 times 3. So nothing leaves the house. We're stuck with that one as well. The square root of 105. When in doubt, please leave them as simplest radical form rather than changing them to decimals. So let's look down at number 3 because this one's dealing with the angles. Remember that if our in-center is point S, then all of these angles are being bisected. So the measure of PRQ, that's this entire angle here, is 8x minus 10. RPQ is 4x minus 14. And PQR is 7x minus 5. Now, one thing that we know, if we ignore everything on the inside, is that the interior angle sum of a triangle is 180 degrees. So if I add all three of these together, 8 and 7 gives me 15, 15 and 4 gives me 19x. Negative 15 minus 14 is a negative 29. All of this needs to equal 180. So 19x is going to be equal to 209. And x is equal to 11. Now, we need to go ahead and plug that in. So if I plug it into each vertex, 44 minus 14 is 30. So that means these are 15 and 15. 88 minus 10 is 78. So that means that this is 39 and 39. And then 77 minus 5 is 72. So that's 36 and 36. And then each of those smaller triangles on the inside also has to add to 180. So that makes this one 129. If I do 180 minus 15 minus 39, that gets me 126. And 180 minus 36 minus 39 gets me 105. And all three of those in the middle should add up to 360 degrees. So just as a recap, our perpendicular bisectors form our circumcenter. It splits, our perpendicular bisectors split our sides in half. And our circumcenter is equidistant to the vertices of our triangle. For our incenter, it is formed by our angle bisectors, so our incenter is equidistant to the sides of our triangle and splits our angles in half. All of these things are going to be very important for you to memorize whenever you're working on your vocabulary. There are a few pages, including the very first page of this document, that will help you to learn that. And then also, if you move down a little bit, this page 10 will also help you to compile your info over the course of day 7 and 8 in our notes.